Today's topic is rotational mechanics. Now let's take a body, any body, and let's fix some axis, and let there be a particle P which goes around this axis in a circular path. Let us say initially it was here, traveled some angle theta. This was, let us say, x-axis. This was y-axis. Then we know that, let's say it is rotating about this axis, then omega, which is the angular velocity, with which this particle P is rotating in the circular path, is defined as rate of change of theta that it travels. Okay, so this is omega. Then we have, what is d omega by d dot? This is nothing but acceleration, angular acceleration. This is angular acceleration, right? Now, like we studied in Newtonian physics, that V is equal to U plus AT, yeah, and S is equal to UT plus half AT square, and V square minus U square is equal to 2AS. This was when acceleration is constant. Similar to this, exactly similar to this, we have terms in rotational mechanics as well, and which is that omega at any time t is equal to initial omega plus acceleration. Instead of acceleration, we have alpha t. Okay, S is the linear distance covered. In our case, it will be theta. Theta is equal to initial velocity, initial angular velocity, half. Instead of acceleration, we will take alpha, and final velocity is any velocity at time t is equal to minus initial velocity square is equal to 2 alpha and theta. So there is a direct equivalence. If you see, this is the rotational mechanics part of it, and this was our linear motion part of it. They are almost exactly equivalent. Now, relationship between linear velocity and angular velocity. Let's see, this point P is moving with velocity v. Then we know that velocity is defined as rate of change of distance, right? And if I magnify this, let us say this was the particle P which was rotating, and it came to this final state, sweeping an angle of theta, and the radius of circle is r. Then this ds we can define as r theta, because r theta is this arc which is covered in time t. Okay, so Since r is constant, we can take it outside. And this term is nothing but omega, as we have defined earlier. So we can say that linear velocity is equal to r omega. So this is how we convert linear velocity into angular velocity. And linear acceleration is equal to dv by dt. Since let's substitute the value of v here. Again, this implies taking r constant outside, dv by dt is equal to, and this term is nothing but angular acceleration, alpha. So we can very well say that linear acceleration is equal to the relationship between linear acceleration and acceleration. This is angular acceleration, and this is linear acceleration. So again, linear component, how is it related to its rotational component? Next topic is torque. What is torque? Everybody must have experienced that you have a door at home which is hinge here, and when you want to open it, you have to push it. You have to apply some force, and as you approach near this axis of rotation, the force becomes more and more. As you move away from hinge, the force required to turn it is lesser. Okay. So what is the relationship? The relationship is torque, defined as tau, is equal to r cross f. Torque is a vector quantity. R is the position vector. From the point of rotation. And F is the force applied. If we see a simple diagram, let's say this is a point O, and you have a force F, which you apply in this direction. Then R vector this is R vector, right? This is F vector. So torque will be R cross F, or this is RF in quantity sin theta. Though torque is a vector quantity, because R is also a vector quantity, F is a vector quantity, and we are taking cross product. Cross product will be a vector, right? Torque is also defined as symbolically. There is another symbol for torque, the same as tau is equal to I alpha. This is another expression of torque, tau, and this I is moment of inertia. And this is angular velocity. You have to be careful. Tau or torque is always applied across about a point or about an axis. Without defining the point of rotation, you cannot define torque. You have to define point of rotation or axis of rotation, right? We just now mentioned that tau torque is equal to I cross alpha, I alpha, sorry. So what is I? I is moment of inertia. Now let us find out what is moment of inertia. Let's take any body. Let this be the axis of rotation. Okay. Then we have different particles. Let us say this is one particle with mass I, and it is at a distance Ri from the axis of rotation. Similarly, you may have this may be M1, this may be M2 at a distance of, let us say, R2. There may be another third particle which is R3 at a distance of R3 from axis of rotation and weighing mass M3. Okay. So what is I? What is moment of inertia? Moment of inertia is nothing but summation of all for each particle, the moment of inertia is its mass into radial distance from the axis of rotation. For this particle, it will be, let us say, mi into ri. So if we take this and integrate over all the mi's, we get moment of inertia. Okay. And r is always the shortest distance of a particle from axis of rotation, and which will be perpendicular distance. The shortest distance of any particle from axis of rotation will be a perpendicular distance. Okay. So if most of the mass lies on the periphery, what will happen is moment of inertia will be more. If most of the particle are lying close to axis of rotation, its moment of inertia will be less. You must have noticed while riding a bicycle or a motorbike in a road in which you are trying to take a turn, and this is your bike. Yeah. You tend to lean inside when you're taking a turn while going around a circle. You tend to lean inside. And why does it happen? Let's see. Let's say you are making angle theta with the vertical. Then let's see what are the forces acting on the cyclist. One is the weight, another centrifugal force, which is equal to mv square by r, we have seen earlier. And there is a frictional force acting between the tires and the road. Okay. Since the cyclist is in equilibrium, so what happens is this force is creating a torque about this point. this torque will be in this direction, while the mass, the weight of the body of the cyclist is going to turn. If we take this moment across this point, it's going to turn it this way. Since the cyclist is in equilibrium, these two torque, if we say this is tau1, tau2, this will be same as tau2. And what is torque created by this force? If we say that this is point A, this is point D, let's make it a fresh diagram. This was the cyclist. Force here, centrifugal force here. This is point, let's say this is point A, this is point D, this is point C, and it's making an angle theta. Mind it, there will be a normal force by the road on this perpendicular to it. Let's call it normal force. Now, if we take moment across this point, this was frictional force. Friction force and normal force will not have any moment because it is passing through the same point. Moment, torque, because of this force will be mv squared by r into its shortest distance from the point of rotation. Shortest distance of point of rotation is CD. This should be equal to the torque generated by weight, which is, this is the force. And what is the shortest distance of this force from the point of rotation? Is this distance AD. Or we can say AD divided by CD is equal to V squared by RG is equal to 10 theta. So if you are in a circular motion, if you are going with a velocity V, whose radius is and the radius of the path, circular path is R, then your bend will be this. This is how much you will be bending. This will be your angle of bending. Linear momentum, in linear motion, we have angular momentum in rotational dynamics. What is angular momentum? Angular momentum is defined by L, which is equal to R cross P. Again, we take the similar diagram. There is a point O, and you have particle moving with velocity V in this direction, and it makes, this is the radial vector from the point of rotation. This is the point of rotation. This is the velocity of the particle. These two vectors make an angle theta. Then we can say this is the position vector from the point of rotation, which was this here. Okay, right? Then, and what is P? P is the linear momentum. Okay. So we can define L as R cross MV, right? So this is our fundamental equation of angular momentum. This is angular momentum. This is the position vector. This is the velocity vector, which is the linear velocity vector. Now in this diagram, if we take this point as O, this point as P, then this position vector becomes OP. So L becomes OP cross MV, which is same as, and if we draw perpendicular from here, and this point is A, then OP cross MV becomes AO cross MV, because AO absorbs these sine theta in the cross product. So L can be defined as now what is this? This is perpendicular distance between velocity vector V and the point of rotation. Okay. So we can say that L is equal to MV into AO, and AO, let's say we term it as R dash to distinguish it from this radial vector. Now, if we call this as the shortest distance between the velocity and the point of rotation, and give it a nomenclature of, let us say, R, mind it, this R is different from this R, but for argument's sake, we make R dash as R. So we can define as L as MVR, right? L is also defined as I omega. And what is I? I we have already seen. I is called moment of inertia. Omega is the angular velocity. So you can define moment of angular moment into two forms. This is when you're talking about linear velocity. And this is when we are talking about rotational angular velocity. In linear mechanics, we learn from linear mechanics, we know that momentum is conserved. Similarly here, angular momentum is conserved. Is conservation of angular momentum. We define another term called angular impulse. Like in linear mechanics, what was impulse? When we strike somebody with a very quick force for a very short while, an impulse is generated. Exactly same way, you have angular impulse as well, which is defined as J, and is equal to a tau, a torque for a very short while. And if you integrate it over the total time, what you get is an impulse. This is what tau is nothing but dl by dt. Tau is nothing but dl by dt into dt. It becomes dl negation from 0 to L1, or it is final angular momentum minus initial angular momentum. This is J. Calculate the kinetic energy of a rotating body. Again, let's take a body which is rotating about this axis, and you have various particles, m1 at a distance r1, maybe m2 at a distance of r2. So the total kinetic energy will be what? Kinetic energy of all the particles put together? And so on and so forth, right? Now, this will become sum of all mi's with their respective velocities by 2, sum it over all the i's. This is equal to, and we have seen it earlier that this velocity, linear velocity, can be converted into angular velocity by this formula, right? Since omega of all the particle is constant because all the particles will be rotating with the same angular velocity, so we take angular velocity outside, and what we are left with is and what is this? Sorry, this was omega square. This portion we have seen earlier. This is nothing but moment of inertia. So this is equal to so kinetic energy of a rotating body is do you see the similarity? If we replace I with m and w by v, You've seen it earlier. Kinetic energy for in a linear motion is this, while kinetic energy in a rotating motion is this. So the terminology, the formula is very much similar in both the cases. Let's find the rate of work done. We know kinetic energy is equal to I omega square by 2, and if we take differential of kinetic energy by dt is equal to power, it will be equal to d by dt of I omega square by 2, right? When we differentiate power, this will be I is constant here, so we take I by 2 outside, we get d by dt of omega square is equal to 2 omega d omega by dt, which is equal to, this gets cancelled, and d omega by dt is rate of change of angular velocity, which is nothing but alpha, right? And we have seen earlier, we write it like this. What was this? This was nothing but tau. So power for rotating bodies moving with it moves with angular velocity v, ends up with tau alpha. Now let us do a small exercise and find out the moment of inertia of a uniform rod whose length is L and it is rotating about its perpendicular bisector. Okay, so what we do is we take a small slice of this rod. Let us say the width of this slice is dx and it is at a distance x from its axis of rotation. Then we can always say small di is equal to small mass into x square, because x is the distance and this is the mass. And what is it? dm we can define as, since we have said that this is a uniform rod of a uniform mass, and if we define linear density as total mass over L, then what happens is, what is dm is proportional to its width, length. So this will be rho times dx into x square, or it is rho x square dx. Now if we want to find out the total moment of inertia, we have to integrate it over full length. Full length will go from, x will go from this point, which is minus L by 2, to this point, which is plus L by 2. So it will go from minus L by 2 to plus L by 2. And what it comes out, rho is constant, and what we get is x3 by x going from minus L by 2 to plus L by 2. This will be okay. And we have already defined rho as this. So we substitute the value of rho. What we get is ml square by 2. Now we took this example to see how do we find the moment of inertia of any body. Now this was only one example. Similar technique you can use to find moment of inertia of various bodies, like it may be a solid sphere, a hollow sphere, it may be a disc, it may be a cylinder, whatever. The treatment has to be done in this fashion, that you take a small unit of mass which is at a distance, and then integrate the whole thing over the whole body. Now the integration may be a simple, or it may be you may have to do it in 3 dimensions, whatever, depending upon the shape of the body. But this was just an exercise to show how you go about finding the moment of inertia of a body. Now next we will take some theorems. One theorem is called parallel axis theorem. What it says is, let us say you have a body and you have found out the moment of inertia about an axis passing through center of mass. Now, if you want to find moment of inertia about any other axis which is parallel to it, and let us say it is at a distance d, then this theorem says, if I say this is an axis A and this is an axis B, then moment of inertia of this body about axis B can be given in terms of moment of inertia of this body against A plus mass time its square of the distance between the two axes, right? So in general, what we do is we write like this: I about any axis parallel to an axis going through center of mass is given as I, an axis going through center of mass, plus its total mass into square of the distance between them. This is applicable for any shape of body. There is no restriction as to how the shape should look like. Okay. Now there is another theorem which is called perpendicular theorem. Again, what we do is we have a body it is rotating in some path. Let us say it is rotating about this axis A, or let us call it Z axis. This is the X axis. We call it anything. Let us say this is X axis, this is Y axis, this is Z axis. Then moment of inertia of the body about one axis is equal to the moment of inertia of the same body if it were to rotate about two axes perpendicular to each other and perpendicular to this as well, is defined as what it means is, if you have an axis Z and if you have another two axes which are perpendicular to each other, then the moment of inertia about one axis can be defined as sum of moment of inertia of two other axes which are perpendicular. Now mind it, this theorem is applicable only for planar object. It means the thickness of object is very small compared to other dimensions, compared to other dimensions. Now we'll take a simple case to illustrate this. Let us say we have a disk which is rotating about this axis, going through its center of mass. This is Z axis, and this is, let us say, Y axis. This is X axis. Now, as per the theorem, what it says is moment of inertia about Z axis is equal to moment of inertia about other two axes which are perpendicular to each other and itself also. Now, if you see this disk, if you were to rotate it like this, or if you were to rotate it like this, moment of inertia is same because of the symmetry. So Iy is equal to Ix, and we can say Iz is equal to 2 times Ix or 2 times Iy. This is just an illustration. Again, to recap, you have an axis and you have two axes perpendicular to each other as well as perpendicular to the axis of earlier rotation. Then the moment of inertia about this axis can be given as sum of moment of inertia about two other axes which are perpendicular to each other as well as it is perpendicular to this axis. Just to recap, in perpendicular axis theorem, condition 1, it is applicable only to planar bodies. 2, all three axes should be mutually perpendicular. All three axes should be perpendicular to each other, like X, Y, and Z. X, Y, Z. Define another term called radius of gyration. If we see the formula, it says moment of inertia of any body can be defined as its total mass times k square, where k is the radius of gyration. Now, this is just a fictitious quantity. Radius of gyration is defined only to simplify calculations. Now, if you see, for example, in case of a sphere, you have I is equal to 2 by 5 mr square. Now, if you compare this formula with this formula, what it says is, if we write it like this, m is 2 by 5 we taken here. And if we call this as k square, then radius of gyration for a sphere will be this much. This again, just to reiterate that this radius of gyration is to facilitate calculations, and if you want to think it of as a phenomena, then you can think it as a concentrated mass, which is at a distance of k from here, because we know that if all your mass is a single point mass at a radius of, let us say, k, which we call as radius of gyration, then its moment of inertia will be nothing but 1 times k square. So it is as if all the mass is situated at a distance k from the axis of rotation, single point mass. I'm sure all of us have some point of the time ridden a bicycle or a mobile. Now what happens when you are on a bike and it moves? There are two rotations which happens. Let's say this is the wheel of the bicycle. One is it rotates in a particular direction, and if this is the center, this also moves in the forward direction. So it has two motions. One is called rotation. Wheel moves, we all know, and we also move forward. Okay, so we translate as well. Okay. Kinetic energy possessed by a moving bicycle. It is given as rotational kinetic energy plus translational kinetic energy. Okay. And what is rotational kinetic energy? We have seen it is I omega square by 2. Now, if this rotation is only because of this kinetic energy on account of rotation is for an I omega, the center of mass, moment of inertia of the body as if it is rotating through center of mass, plus translation kinetic energy we have seen in earlier linear mechanics is mv square by 2. Okay. Then this is same as moment of inertia through if an axis going through center of mass, omega square by 2 plus V we have already seen is r omega, right? So if we take I, sorry, if we take half omega square common from both of them, what we are left with this, and this will be taken out. Okay. Now, this is the moment of inertia of a body passing through the center of mass, and this is mr square. Now, if you see this diagram, this is our center of mass, this is our point of contact, which is at a distance of r from here. So, and if we apply our parallel axis theorem, what it says that you have an axis through which the body is rotating, and if we add mr square to it, we get an axis which is a distance r away from the center of mass, which becomes this. That means this whole term, if we take center of moment of inertia, this becomes the moment of inertia about this point P, which is the point of contact. So this becomes I. This is point of contact about right. Now you must have seen on an icy road, while you're moving, you slip. Or if you are moving and you suddenly somebody comes in front of you, you put your brakes, you hard brake your vehicle, and in this case what happens? You skid. Now we will analyze these two phenomena with respect to a normal phenomenon. When you are riding a bike normally, which is neither slipping nor skidding, then suppose your wheel is rotating with velocity omega, then the velocity of center of mass will be equal to omega r. Here r is this is r. This is the velocity of center of mass. If the center of mass goes forward with this relationship, then there is no, this is pure rolling. Meaning by no skidding, no slipping. You are in a pure rolling state. Okay. Now what happens? Your wheel is rotating fast, but you are not moving forward in the same ratio, which means that your tire is slipping. We call the tire is slipping, right? So in case of slipping, the velocity of center of mass is less than what it should have been in case of pure rotation. Okay. And conversely, if you hard brake, you skid. Now what happens when you hard brake? You lock your wheels. When you lock your wheels, what happens to omega? It becomes very, very small, but your speed speed is high. So in case of skidding, center of mass is much higher than this relationship. So these are two phenomena, slipping and skidding. Now, if you are riding your bike without any skidding, then we know if this is the R radius of your tire, you are rotating with angular velocity omega, then center of mass, or you will move forward with the velocity or R omega, right? Now what happens to the velocity of a point here, A? Velocity at point A will be twice as velocity of center of mass. Velocity at the top of this tire will be twice as much as the velocity of center of mass. Let's analyze motion of a ball going down an inclined plane. This is a ball or a sphere, we can call it, is going down the inclined plane, and it has a radius r. Now what are the forces acting on this? What are the force acting on this is mg. Yes. There's another force acting in this direction, which is the frictional force. Okay. Then there's a force which is acting perpendicular to this, called the normal force. Now we have seen earlier many times that this force pulling it down is mg sine theta, and the force, the component of mg in direction perpendicular to this plane is mg cos theta, and which is neutralized by the normal reaction of the plane. Okay. Now see various component of torque. Then the torque generated by this force, frictional force, is R cross F. This is the frictional force, and this is the torque created about center of mass. Is also equal to, we know you can define torque in two fashions. One is this and another is I alpha. In I alpha is nothing but A by R. Okay. So if we take RF as I for a solid sphere is 2 by 5 mr square A R. Okay. Then what happens is, one of the R gets cancelled by this R gets cancelled by this, so we are left with F equals Now, we also know that mg sine theta if we take this body, there are two, this force has been neutralized by this force, which was in the perpendicular direction. And along the plane, there are two forces acting. One is this force and another is this force. So this is the acceleration, linear acceleration. Okay. And mg sine theta, f we have already calculated here, is 2 by for a solid sphere. This I was for a solid sphere. 2 by 5 ma is equal to ma of what we get is mg sine theta is equal to and cancel out from there. So you get A is equal to 5 by 7 g sine theta. Which means that if a solid sphere is rolling down an inclined plane, its linear acceleration of center of mass is given out by this formula. Okay. Now, how can we say that this will be rolling or not rolling? All right. What we know is that this was the friction. We calculated like this. And what is the maximum friction that can be generated on a moving body? This is nothing but u times normal force, and normal force is mg sine theta. That means if we talk about maximum frictional force that can be possible is this, that means the maximum acceleration that we can get is this. So A max, what we get is, sorry, this will be not sine theta, this will be cos theta. M gets cancelled out. So this max is right. This was cos theta. So mu, what we get is now if we put the value of A from here, what you get is what you get is 2 by 7 tan theta. We have seen that mu is equal to 2 by 7 and theta. Which means that if the inclined plane is inclined at theta degrees, then this should be the requirement of mu. This is the case of pure rolling. If the Planck can provide us this much of mu, well and good. You end up with pure rolling. So what could be the cases? That mu actually that can be provided is greater than or equal to the requirement. This is the minimum requirement. This is minimum requirement. In such case, what we will have is pure rolling. If this cannot, if the actually that can be provided is less than our requirement, what will happen? Rolling will not happen and it will result in slipping.